Hello, my name is Joshua Garcia, and I am an assistant professor at the University of California, Irvine, and I am giving this talk on our paper entitled A Comprehensive Study of Autonomous Vehicle Bugs. This work has been conducted in collaboration with Nanjing University. So, autonomous vehicles are becoming pervasive and ubiquitous. The companies behind these autonomous vehicles are already claiming millions of miles driven and thousands of rides given. These AVs are cyber-physical systems, so they involve both software and physical components that interoperate and interface with the physical world. Because these vehicles transport living creatures on open roads, the faults, defects, and bugs behind them can easily result in serious injury or loss of life, like the one that occurred here in Tempe, Arizona in 2018, where the first pedestrian fatality due to an AV occurred. This involved a Uber AV driving around 10 p.m. at night. At that time, the victim was crossing a street, pushing her bicycle. The AV failed to detect the victim in time, resulting in a collision that resulted in the loss of the person's life, unfortunately. So AV bugs they're not well understood. There are no previous empirical studies of AV software bugs. So what that means is that the root causes behind such bugs, the kinds of errors or driving errors that may manifest due to them, or even the parts or components of these AV software systems that are most affected by these bugs. These are all issues or aspects of such systems that are poorly understood. One of the reasons why there are so few, or in fact no, studies of such AV software systems is due to the lack of, one, the number of such existing systems, and two, the fact that previously none of them were industrial grade. However, this is no longer the case with the release of two software systems, Apollo and AutoWare. Apollo, which is an open source software system that is created and released by Baidu, one of the largest AI and internet companies in the world, has reached a mass transportation agreement with Volvo and Ford. AutoWare, which is built by the AutoWare Foundation, has been adopted by the US Department of Transportation and involves a wide variety of companies including Intel, ARM, LG, and Huawei. So using Apollo and AutoWare, we conducted a comprehensive study of AV bugs and their characteristics. We looked at over 16,800 commits and nearly 500 AV bugs. We identified 13 root causes, 20 symptoms those root causes can exhibit, and 18 categories of AV software components that may be affected by these bugs. From our study, we suggest future research directions on software testing, analysis, and automated program repair for AV software systems specifically. To better understand the rest of this talk, it's important to understand the software architecture of autonomous vehicles. So these vehicles take as input a variety of sensor inputs, for example, LiDAR, radar, and GPS. They perform perception, for example, object detection and tracking, localization, determining the vehicle's position in the physical world. Based on this information and a high-definition map, the autonomous vehicle can make predictions such as future trajectories of the vehicle and obstacles. It can plan its movement and send this information to control actuators such as the steering wheel, brake, and gas. To conduct this study, we performed an open coding methodology where we focus on closed and merged pull requests that involve bugs or fixes, leading us to our 500 bugs that we studied for this particular paper. Using this methodology, we came up with 13 root causes, including incorrect algorithm implementations, numerical computations, and configurations. 20 bug symptoms, many of them involving driving functionalities such as stopping and parking, speed and velocity control, and vehicle turning and trajectory. We also focus on 18 AV components that can be affected by these bugs, including the top-level components I previously discussed and their subcomponents. Using this three-way categorization, we studied 5 research questions. For this talk, I'll focus on 3 of them, starting with the bug symptoms produced by root causes. One of the more interesting findings for this particular research question involved the incorrect algorithm implementations. These are algorithms that are specific to the domain of AV software systems and focus on components such as perception, localization, prediction, and planning. They involve many lines of code, on average about 100 lines of code, and they cause all 8 types of driving symptoms. And these particular root causes are going to be challenging for existing bug localization and bug repair to automatically handle due to the number of lines of code and the domain-specific information. So there's an open research challenge there. However, existing bug localization and repair may work well on the 25% of bugs for which there are only about 20 lines of code or fewer involved in the root causes, such as incorrect assignment of variables, conditional statements, or conditional logic. And these particular types of root causes actually affected or produced about 16 of the 20 AV bug symptoms. Another interesting research question involved the frequency of bugs in AV components, which can help direct software researchers and practitioners to the components that are most buggy and deserving of their attention. I'm going to focus on the medium to high components in terms of frequency of bugs. In particular here, let's focus on perception in particular at the top left with its 83 bugs. Perception is interesting because many papers already focus on perception, since perception involves a lot of deep learning and machine learning. What's more interesting is that other components, in particular planning here, has the most number of bugs by a large amount, 135 specifically. And planning actually involves 60% of bugs that directly affect driving functionality of AVs. And what this means is that most of the bugs affecting driving functionality occur in planning, meaning many of the bugs there can lead to driving errors, serious injury, and even death. And in fact, planning is one of the components that is not really studied in existing software research. So future research should really focus on components like planning. So in conclusion, I've given you a brief preview of our comprehensive study characterizing AV bugs. I've only gone over a few of the 16 major findings in our paper. I encourage you to read the paper to learn more about those findings. And also, our current and future work are focusing on test generation and test oracles for AV software systems, particularly involving the planning component. We're also refining the bugs from this study so they can serve as a benchmark data set for automatic program repair for AV software systems. So thank you for your time and attention.